Alrighty, for those of you who don't know me, I'm Jamin, and I will be doing section 2. Alright, in this section, pages 42 to 96, we are going to be looking into geometry, right? We're going to be explaining geometry algebraically and looking at it on 2D as well as 3D planes, right? Um, in this little lesson right here, we are going to be going over the Pythagorean theorem, how to get the area of triangles, right? Special right triangles, which I'll go into in a little bit, which are 30, 60, 90 degree angles, 45, 45, 90. Midpoints of segments, slope, right? Distance, okay, distance of these, of say, points on a 2D plane, right? The distance between, say, for instance, this point here and this slope, right? And perpendicular lines, okay? Lines that are dead center of each other and create a 90-degree angle on either side. Right. And we will, of course, go through this and explain the formulas, and I will give examples showing this and proving this. Alrighty, let's get right into it. Let's start by looking at a square. Your standard square. Alright, let's say each of these side lengths are 1 as a reference point. That won't matter for now. But we know that a square is comprised of 4 corners, right? Each equaling 90 degrees. 90 plus 90 plus 90 plus 90 equals 360 degrees. So we can safely say that a square is equal to 360 degrees, right? When you cut a square in half, though, you get 2 triangles, 2 right triangles, right? 2 right triangles. And when you do that, you cut it in half, you get 180 degrees, okay? Each triangle is equal to 180 degrees, right? And is defined by, to be called a right triangle, defined by a 90-degree angle, always, right? And we'll get into special right triangles and how that affects them and the formulas that go with it. Alrighty, using those measurements as a reference point, let's put our little reference square up here, our little 1 by 1 cute little box over there. All right, let us take a look at a 3 by 3 square now. All right, 3 times 3 is equal to 9. So we can say that this 3 by 3 square, this box, has an area of 9. All right, now I'm going to draw a square in here, an inner square, right? And what we're going to try to find is we're going to try to find the area of the square within the square within the square, right? First off, using the information we just saw, we just looked at, right? Each one of these units is equal to 360 degrees, or each square is at least, and we know that each corner is equal to 90 degrees, right? So we know that that each of these outer triangles that are formed, I'll draw that in really quickly. Each of these outer triangles that are formed, okay, are equal to 180 degrees. And all triangles are, but we know for a fact that these are 90 degrees. Okay. So to figure out what's in the center, we are going to figure out first what is in the center of our triangles, the outside of the square. Okay. And we're going to figure that out using a neat little formula to calculate the area of our triangles, our little right triangles. Okay. Let me write it out real quickly. I'll explain the variables. No, that's not it. Okay. So 1/2 times b times h. What does that mean? Right. We have 1/2 times b, which is the base. Right. We're going to define this as the base. Right. This section right here is the base, and it is 2 units. Okay. 2 units, 1 by 1, and times the height. right, which is this little section over here, which is 1. Okay, so let's plug that in real quick. So we have 1/2 times the base, which is 2, times 1, which is the height. Okay, now what's that? 2 times 1 is 2. 2 times 1/2, that's 1. Okay. All right, and we can safely say that all of these outer triangles, these outer right triangles, are equal to each other. Okay, we can say that, right? So what we're basically going to do is we're going to add the area of these 4 right triangles together, right? 1 plus 1 plus 1 plus 1 is equal to 4, okay? And we're going to take that area that we figured out over here, and we're going to subtract it from the original. And by doing that, we can find that the area of this inner square is 5. Now, this was an interesting problem because you don't normally find the square root. That is what you would call this, the square root of the number 5. You find the square root of 9 really easily. It's 3, right? And I'll show you a list of numbers, right, that it can be easily computed, right? Numbers like 1, 4, 16, right, 9, 25. Okay, these can be squared very easily. But numbers like 5, like we have over here, you have to be a little bit more creative when you're taking on a visual stance. Okay, and so that's what we have represented over here. Okay. Now we are going to look at something called the Pythagorean theorem that I said earlier, right? And this Pythagorean theorem represents the side lengths, right? How to find the side lengths of our right triangles. So let's draw a triangle really quickly. Right triangle. And let's define its sides. Let's define its legs. Okay. First, we can define as this being a leg, right? And as this being a leg. Our longest side will be known as the hypotenuse. Okay, we'll call that the hypotenuse, our longest side, right? Anything that is not the hypotenuse in a right triangle is a leg, right? It's the shorter side, okay? Now, let's write out the equation for the Pythagorean theorem, right, to better understand what it is. Okay, so let's write that out really quickly. So a squared, I'll fill in the variables, with the meaning of the variables. A squared plus b squared is equal to c squared, okay? So if you don't already know, or you could guess, we will verify, no, we won't verify. We will fill in A and B, supplement them as our legs, right? Our shorter legs, the ones that are not the hypotenuse, right? So A and B are these 2 legs, right? And then C is our hypotenuse. That's this one over here, okay? So what do we do with this equation? Well, let's put in a couple numbers. Let's plug in some numbers. Let's say we have the numbers 3, 4, and 5. You'll see very soon that these numbers are picked purposefully. 3, 4, and 5. Well, let's plug it in. A squared, which can be defined as 3 to the power of 2, right? Plus 4 squared, or b squared, can be defined as 4 to the power of 2, is equal to c squared, which can be defined as 5 to the power of 2. Now let's write it out. What's 3 to the power of 2? That's 9. Right? These are easy squares. That's 9. Okay. Plus 4 to the power of 2, which is 16. Right? What does that equal? That equals 25. Okay. And we can tell this already right beforehand because the square root, 5 to the power of 2 is equal to 25. Right? And you call numbers that fit this criteria simply in the Pythagorean theorem, triples, right? You will find some numbers because you will find some numbers that don't fit it very nicely. For instance, you will have an equation such as, let's say, 2, the square root of 2, right, plus 4 is equal to, say, 5. Sorry, squared. Okay, that's not very pretty. Okay, that's not very easy to handle, right? Not right now, at least. Not right now. And so that's why previously we would call those Pythagorean triples. Okay, now we know how to look at a right triangle on the 2D plane. Now, what about a 3D plane, right? Let's draw in a cube really quickly to help us define this. All right, so I'm going off of the book right now, right? One of the book problems, okay? So if you'd like to follow along, you may. It's a poorly drawn cube, my apologies. Okay. All right, so the question is, can a 5-foot pole fit in this box? And let me give you the dimensions of this box. The dimensions being the length, the width, and the height. Right? 2, 3, and 3.5. Okay. Now, how do we prove, or how do we figure out, using the Pythagorean theorem, that you can fit this pole? I don't know why you want to fit a pole, but hey, that's just the problem. Why you'd want to fit a pole that is 5 feet long inside of this box with dimensions 2, 3, and 3.5, right? How do we do that? Using the Pythagorean theorem. Well, let's get creative. Let's draw in our own little triangle, right? Let's make a diagonal, okay? And you call these 3D, three-dimensional diagonals, right? Let's draw this in like that, and we know the height, which is 2. Let's just draw it in again, though, right? We can see that this itself is a right triangle, right? And we're trying to figure out if this length will fit, right? Okay, so one step at a time. What do we do first? Let's check out this one, since we already have these two sides, right? And we can now figure out this side, right? Let's plug it in. All right. Let me put the reference up here. A squared plus b squared is equal to c squared. All right. That's our reference. All right. Now, having that up there, I'm sure you guys can do it. All right. 3 is our leg. 3.5 is another leg, and we will assume, and we know, that this will be our hypotenuse. So let's do that really quickly. Alrighty, so this will be defined as 3 squared plus 3.5 squared is equal to c squared. Alrighty. Oh, sorry. Okay. I like arrows. I'm going to be drawing arrows a lot because I end up running out of room very easily. I'm not the best organizer. Alrighty. So let's do this real quickly. 3 to the power of 2 is 9, right? Plus 3.5 to the power of 2, which I believe is 12.25, right? You add those together and you get, what is it? 21.25. All right, what do we do with this? Well, we take this number as our hypotenuse of this diagonal, this three-dimensional diagonal, and we put it right there. Let me erase this. I do this to myself too much. Let's erase some stuff really quickly. Alrighty, what is the number? Okay, 21.25. That is the diagonal for this right now. Right, now what do we do next? Do we have any more lengths that can help us define our hypotenuse for this right here? The pole. What else do we have? We do have this. So let's check this out. Since we have 2 of our lengths here and here, all right, these now become our legs. These were our legs. Now these are our legs. Now that this is defined, now that we have 2 points defined, okay? You have to have at least 2 points. Sorry, not 2 points. 2 lengths defined to be able to do the Pythagorean theorem. And now that we do, which it is 2 and 21.25, we'll do it over here. So let's get some space. Alrighty, so we can write out in the theorem, the Pythagorean theorem, 2 to the power of 2 plus 21.25 to the power of 2 is equal to, well, let's see, 2 to the power of 2, which is equal to c squared. Let's just do that real quick. 2 to the power of 2 is equal to 4. And this is going to be a really interesting number. So let's do this. Let's do this. Let's put a little square root at the top of that. So these cancel out. All right. So we keep it that. We keep it at that. All right. So we end up having 4 plus square root of 21.25 squared. All right. What do we get? We get 25.25. All right. We finally have our length. We finally have our last length, the length of the pole. Well, actually, no. My apologies. Well, yeah, we do, but we have to simplify. 25.25. We have to take the square root of this as well, right? And it ends up being about, I think it was 5.1 or something like that, about 5. So yes, this 5-foot pole can indeed fit inside of this cube, this three-dimensional box, the dimension of this three-dimensional box. And that is one of the ways to use the Pythagorean theorem for this. Alrighty, now let's take a look at, now let's move on to, oh, I forgot one thing, my apologies. You know how I said there are Pythagorean triples, right? Numbers that fit very nicely to create a number that is more friendly, user-friendly, right? There are also Pythagorean theorem quadruples. I think that's what it's called. Let's write it out really quickly. And this defines 3D dimensional objects, similar to the similar to what we just did. Right? So let's check it out. And this formula can go, and we can use this formula to compute the what is it? The equivalence of c squared. Let me write it out really quickly. It'll make more sense in a second. So this is what a Pythagorean quadruple would look like. Here we go. 2 to the power of 2 plus 3 to the power of 2 plus 6 to the power of 2 is equal to 7 to the power of 2. All right, that is a Pythagorean theorem quadruple. All right, and this is what it would look like in the three-dimensional formula. Let me write it out real quickly so it makes a little bit more sense to you guys. All right, so it'd be the length squared plus the width squared plus the height squared. Okay, that's what that would look like. And going back to our little, oh man, I'm gonna draw another bad cube. Going back to our cube, right? That is the dimensions for this little thing, right? Oh, I botched it yet again. That is the dimensions for this right here, which is equal to, sorry, d to the power of 2. Okay, now that we have that out of the way, let us take a look at the coordinate plane, right? The coordinate geometry. All right, so we are going to first be looking at midpoints of segments. Okay, so let me draw a little graph. Slap a little graph, all right, and we're gonna randomly pick a couple points, right, and we're gonna draw a random line. Okay, this. Oh no, sorry, my apologies. I'm getting ahead of myself. No, this is our line segment. I'm sorry, it's still out of view over there. This is our line segment. Okay, there are two endpoints, right? Two endpoints define line segment, and what we're trying to find is the midpoint. Right? Where's the midpoint? Right? How do we figure that out? Well, let's say let's give these imaginary points on the graph. Right? Let's give these coordinates. All right. So let's say this is 5, comma, -3. Okay, and let's say this one is -3, comma, 6. Right? How do we figure that out? Oh, you can't see it. My apologies. All right, let's write it down here. This one right up here is -3, comma 6. Sorry about that. All right, how do we figure that out? Well, like most things, or the things we have looked at in the past, we have been using algebra to figure things out. Algebra. So let me write out this neat little formula. All right, we got this neat little formula to help us figure out what to do. All right, so let me write it out real quickly, and then I'll define each of the variables. So we have x1 minus x2, right, over 2, comma, y1 minus y2 over 2, right? And this right here is equal to the midpoint. Now what does this mean? Now these x's, right? These x's are equal to these over here, right? -3. Our x's in this case would be -3 and 5. Okay, and we will subtract those two together and divide by 2 to then get our x coordinate, right, for this, right? And then we have our y's. Get another coloring. We then have our y's. In this case, it would be 6 minus -3. Okay, 6 minus -3. All right, and we will divide that by 2 after subtracting it, right? And we would get our y coordinate. So this is essentially our x, and this is our y. All right, and that is how we find our midpoint on the light segment. Okay, now let us look at slope. But first, how do we define slope? How do we define slope? Let's use a vocabulary word that I like to use to help us define it. Slope is the rise over run. Sorry, the rise over run, right, on a graph of a line. Okay, what does that mean? Rise over run. What does that mean? Right. Let's say we had a slope, right, and we're looking at the 2D plane. Right, this is the two-dimensional plane, right, the two-dimensional coordinate plane. Let's say we had a slope of, let's say 2 over 5. Okay, so this is what we do. Draw that out really quickly. So let me write these down really quickly. Alrighty. So it's a little self-explanatory. Rise over run. Well, let's look at number 2. Let's look at this right here first. All right. First, we look at if there's a positive or negative sign right here. If it's a positive sign, it's going up. If it's a negative sign, it's going down. Okay. So we rise 2, right? And when we rise, we go up on the y-axis, and when we run, we go along the x-axis. So we're rising 2 on the y-axis from the origin, right? Since we don't have a defined point in this case, from the origin, okay, or from behind here, whatever we don't know, of course, where we started. From the origin up to 1, 2, and then over 5. 1, 2, 3, 4, 5. Okay. Okay, right. And we just continue that, and then from this point we do that again, right? Up to over 5. And I'm getting in the way, but eventually, in the way of my stuff, and eventually we would have a line, right? It doesn't look very nice because I didn't measure it properly, but it would end up looking something like that. A little bit more pretty than that, but you know, something like that. That is what slope is. And you would call this line collinear because the points meet on the line more than twice. Okay. Now let me just find something that's non-collinear to give you an example. Something that's non-collinear would look something like this. This is again a coordinate plane, we're looking at, okay? Let's say we have 3 points, right? This kind of looks like a triangle if you put them up, but we will ignore that for now, right? If we were to connect these points, let's use a different marker. If we were to connect these points, right? There are never 3 points on the same line, right? And that therefore it is not linear, is non-collinear. Alrighty, I don't think I defined that very well, but I'm sure you guys will fill me in class when I present or when I give you a quiz. Alrighty, so how do we figure out what the slope is? How do we figure out what slope is? All right, well, let's define slope first. I already defined it, but I said something about rise over run. Let me write that out again. Rise over run. You got an idea. I gotta be aware of my surroundings. Rise over run, right? You got a little taste of what it is, okay? Now, what's the equation for this, right? What's the equation for this? Let me write it out really quickly and tell me. Well, don't tell me, obviously. I'm talking to myself in the camera. If you're familiar with this equation, y is equal to mx plus b. Right. Okay. Now, let me say and show you that m, right, in this case, is our slope. Okay. M is our slope. All right. And m is basically the change in the change in y over the change in x. Let me show you what that looks like. It is equal to the change in y over the change in x, not the triangle over y, not the triangle over x. That's just a symbol for change, right? And which is equal to, right, y1 minus y2 over x1 minus x2. Alrighty. And that is basically slope in a gist. Alright. What do we look at next? We will look at the formula for the radius of a circle, right? The coordinate equation, right? So let's check this out. So if I were to write out the equation really quickly, and I'll plug in as I draw out the graph, and things will make sense. All right, so we have x minus a squared plus y, that's a parenthesis, minus b is equal to r to the power of 2. Now what does this mean? All right, well, I'll show you up here. Say let's start by defining a and b, right? A and b are coordinates, okay? A and b are coordinates, and we're defining this the coordinate equation for a circle, right? Which has a radius of 4, right? Right, it has a radius of 4 units. So let's draw this graph. Let's see what this actually looks like, okay? I'm just going to draw it's not on there. Draw a rough estimate of what this would look like, right? All right, so this circle is centered at the coordinate, let's say 5, 2. 5, 2. Right. That is our A and B. So that's what would go here. So our A would be 5, and our B would be 2. Okay, so it would then be x minus 5, power of 2, plus, what do we have here? Y minus 2, which is b, power of 2, equals r to the power of 2, which is 4. R is the radius. I should have clarified that, right? And so r to the power of 2, or 4 to the power of 2, is 16. Right, and so that is the equation for this right here. Now we can do just about the same thing looking at a sphere, and it looks really similar to a lot of the other things we've done, right? when you look at three-dimensional equations, right? Like the Pythagorean theorem or the distance formula, which we're going to be doing soon, right? It's usually x, y, z. Okay, so in this case, well, let's take away that. All right, let's just add something. Let's add it on to it. Right, so it would be z, sorry, z minus c, right? A, B, C squared, which is equal to r squared. Alrighty, and that is how you find the 3D or spherical radius on the coordinate plane. My bad. Okay, now let's take a look at, let's see, distance. All right, we're going to take a look at distance and the formula for distance. Let me write that out really quickly. The formula for distance, which is a fairly simple one. And once we understand it, we can easily compute compute and put our numbers in there. All right, so it is x1 minus x2, right? The power of 2 plus y1 minus y2 to the power of 2. Okay, so knowing this, right, we have this formula here. Let me make a situation. Let's make a situation so we can fulfill this formula. Okay. Let us say we have a perpendicular line going through the origin. And let's say it has a slope of y is equal to 2x plus 1. And we know what a slope is now, right? 2x is the slope, or sorry, 2 over 1 is going to be the slope of this line, right? And we want to know the distance between the slope of this line and this point right over here. We're going to figure this out, right? Which is 8, comma, negative 5. How do we do this? Well, we use this distance formula right over here, right? And I'm going to start substituting, okay? Since y is equal to 2x plus 1, right? Alright, that is our y, okay? And it is at 0, so it would be 0, comma, 2x plus 1. And this will make sense in a second, right? So we have the coordinates, how do I say it? 0, comma, 2x plus 1. And we have 8, comma, negative 5. Right? Okay. Now I'm going to make some space so we can start getting onto this equation. All right. Yeah. Okay, so we have, and if we look, oh, it's not there anymore. I just erased it. But if we plug them in successfully to our distance formula, right, we would then have, can I ahead of myself? We then have x minus 8, right? X plus 2x, right, plus 1 plus 5. Because these are our y's, and the x is unknown for this. Sorry, the power of 2. Right. After doing that, right, let's crunch it a little bit. We then have x power of 2 minus 16x plus 64. There we go. Plus 2x plus 6. Sorry, running out of room. All right, and then we go from there to here. A lot of simplifying, a lot of moving and reshuffling numbers around. All right, doing the grunt work of this algebraic part of geometry. All right, 16 plus 64 plus 4 x squared plus 24 plus 36. Okay, and then our final answer is it still on screen? Okay, it is. Our final answer would then be 5x squared minus 8x plus 100. All right, that is for sure a mouthful. And so this equals the distance, right? But we don't have to just stop there, right? We can go for the vertex form of this, or the parabola form, the way it would look on a parabola, right? Which is, if I write that over here, y is equal to ax squared plus bx plus c, right? And that's basically the form we have right here. The 5x squared is ax squared, right? We have 8x over here, that's the b, and the c is the 100. Okay, so we'll just start plugging things in. Okay, I'll erase everything up at the top over here, and we can get going on that. Okay, then we plug that in really quickly, right? And this form right here, the vertex form, right, is located at x equals minus b over 2a, right? And if we were to plug that in, right, and let me write that out. So this is located at minus b, remember it's the same variables, minus b over 2a. And let's plug that in really quickly. Let's say, well, we know for a fact that this is our a, and then this is our b. So let's do that really quickly. So this is equal to minus 8, right? Which ends up being plus 8 because it's already a negative, right? And we have 2 times 5, okay? Let's see what we get. All right, so this is equal to 8 over 10, which is also equal to 4 over 5. All right, so then this right here, once you get this, you then go back and plug it in and you'll get your y, okay? And then you'll find the exact coordinates, which should be 4 over 5, comma 3 over 5. Yeah, that's what it is. Okay. And this right here is the no, not the distance. My apologies. And this right here, when plugged back into the distance formula, along with the original coordinates, which was the original coordinates from the point, which was 8, comma negative 5. All right, when plugged into the distance formula we were looking at earlier, we finally get the distance between our line, our linear line, and the point 8, comma 5, comma negative 5. And so let's do that really quickly to finish this problem. Distance, the distance formula, let's write that over again, right? X minus 1, so in this case our x's are 8 minus 4, oh, sorry, my apologies, plus 4 over 5, right, squared. And then we have, right, plus our y's, which are over here, which are negative 5 plus 3 over 5 squared. Okay, when we do some simplifying, we would then end up getting a big number, big number, the square root of 484 over 5. And we do that one more time, simplify it again, we would get 22 over the square root of 5. And then that, my friends, is the distance between this point right here and this line right here. Whew, that was a long equation. Sorry to put you through that. Right, when finding the slope of a line that is perpendicular to another line. So let's draw the graph really quickly. All right. and we're on the 2D plane, 2D coordinate plane, right? When you have a line as perpendicular to one another, and they make right angles, right, 90-degree angles, they're perpendicular for a fact, right? Right? And we know one of the slopes, okay? And let's say this slope is let's say 3x, okay? The slope is y equals 3x, right? The easiest way to go about it is just flipping it, right? So that means this one would be the exact opposite of what this slope is, because they're at a perfect intersection that create a 90-degree angle, right? When crossing over each other, right? So then it would be y is equal to negative, right? Since it's positive, we have to flip it, negative 1 over 3. Since this right here is 3 over 1, right? It would then be negative 1 over 3. So that is how you find the slope of an opposite, the slope of a perpendicular line. And that sums it up for section 2 of geometry, pages 42 to 96. I'm not sure if anybody noticed or if you guys noticed, but I had to cut out a couple of stuff. I had some technical issues. My storage kept on running out. I had to resolve that. So this is a little pulled together. It's a little interesting. Anyways, I hope you guys understood my video. I'm sorry if I wasn't clear on certain points. Please feel free and do so, actually, to tell me things that did not seem super clear, so I can make sure I do a better job next time. Not saying that, thank you, and yeah, adios.